Hello everyone, welcome to CSCN 503, Introduction to Communication Networks. This is Dr. Amr Al-Mugi.
Internet to the other. We basically opened the black box that we call the Internet core, and we saw that the Internet is actually made of a bunch of autonomous systems that are interconnected, and an autonomous system is managed or is identified by an autonomous system number and is managed by a single administrative entity. We also discussed how packets actually go from one place in an autonomous system to the other. So we said that within one autonomous system, the packet first makes its way through something called the border router, and then it jumps from one border router in one autonomous system to another border router in a second autonomous system, and then it makes their way through the second autonomous system until it reaches a second border router where it jumps to a third autonomous system and so on until it reaches an autonomous system that has actually the destination where it makes their way to that destination. Okay. How does networks forward the packets within an autonomous system and from one autonomous system to the other? Through a collection of routing protocols. And we said that we can categorize routing protocols into two main categories: the IGP or Interior Gateway Protocol and EGP or Exterior Gateway Protocol. Okay, and we started discussing last time the Interior Gateway Protocols. Basically, we discussed that all interior gateway protocols work by abstracting the network as in a graph, as we see here. And so how do we actually get from one place or one node in this graph to the other? One way is to do something called static routing, where a network administrator manually implements a route on the routing table of a router. So for example, the network administrator would go in this figure to router U and say, in order to reach Z, the next hop would be X. And then they would go to router X and say, to reach Z, the next hop would be Y. And then they would go to Y and say, the next hop is Z. Okay. Obviously, this only works in small networks. In large networks, we want this process to be done dynamically. We want the routers to be able to figure out the path themselves and to figure out basically how to reach other devices and what is actually the best path if more than one path exists. And we discussed that routers do that using one of two types of internal gateway routing algorithms. They are called link state and distance vector. Both of these are types of IGP protocols. Okay, the link state is the one that actually discovers optimum paths. So every router will have a full view of the network, will have a view actually of this graph. And the cost of traveling or sending a packet over each edge. Okay? Whereas decentralized or distance vector protocols will know actually a path from any place in the network to the other, but this path might not be the optimum one. Okay? We discussed that in link state algorithms, there will be an algorithm running within the routing, the IGP routing algorithm, to find the best path, given that the full topology of the network is now discovered. And we discussed this algorithm, which is called Dijkstra's algorithm, and how the routers actually use it to find the best path or the optimum path from any place to any other place in the network. We will start our discussion today of one type of IGP routing algorithm that actually implements Dijkstra's routing and is a type of link state algorithm, which is called the Open Shortest Path First, or OSPF. Now, OSPF is a link state routing protocol. It basically finds the optimum paths, and every router that is running OSPF will have actually the full view of the network. So the way it works is that routers will periodically send something called link state announcements. These link state announcements will have the entire routing table of a router, saying basically, in order to reach this router, the cost is X. And so let's say, for example, you have this router that has just been plugged in the network. It will say that these are the networks that are directly connected to me. And so to reach them, you can actually send the data to me. Now, other routers will receive this routing table and will now know that these three networks here are reachable through router X. Okay? And now, when the second router sends its link state announcement, and so this information keeps propagating in the network, And so every router will know how to reach every other router, and they will also know the cost of sending over each link in this case. Okay. OSPF is quite flexible. It supports several routing metrics such as reliability, throughput, and delay. So the cost that you see here in this figure can actually be representing different metrics. It can be representing delay of sending over a link. It can be representing reliability or bandwidth. OSPF allows the network administrator to define what the metric actually represents. Okay. Now, the other very important feature in OSPF is that OSPF achieves some kind of compromise between link state and distance vector routing. First of all, what is actually the importance of having something like a distance vector routing protocol if it does not discover optimum paths? Basically, we see here that in order for OSPF to operate effectively, the routers have to periodically send their link state announcements. They have to periodically send the entire routing table. This consumes a lot of bandwidth and consumes a lot of overhead because this is not actual user data. It's just control data that is used to support the routing protocol. So we want to actually minimize it. In a link state algorithm, if the network is too large, imagine, for example, that you have 100 routers in the network, all of them periodically sending link state announcements. This will consume a lot of the resources of the network itself. So it is not desirable if you have a very large network. On the other hand, distance vector routing, they don't send the entire routing protocol, routing table. They only send when they detect changes. So it consumes less overhead, but in the same time, it doesn't actually find the best route. It just finds a path from any device to any other device. Okay, but it consumes less overhead, and they are simple and require less processing at the routers. Now, OSPF has a compromise between the two. It divides the network, the entire network, into areas. Okay, and defines one area to be called area 0, which is the backbone. Now, within one area, routing is optimal. That means Dijkstra's algorithm runs within one area. So if a device within one area wants to send a packet to a device in the same area, the path between them will be an optimal one. What happens if a device in one area wants to send a packet to a device in another area? For this to happen, the packet first sends the router first will send the packet to the backbone or area 0. Area 0 will forward it to area 2, and area 2 will then forward it to the destination. This is shown in this figure. Here you have an OSPF system running over 3 areas, where you have area 0 and then area 1 and area 2. Within area 1, all paths discovered from any source to any destination, as long as both source and destination are both in area 1, will be optimal according to Dijkstra's algorithm. What happens if a device in area 1 wants to send a packet to a device in area 2? Okay. What will happen is the router will find an optimal path to the area router. And then the packet, using Dijkstra's algorithm as usual, and then the packet will be routed to the border router, okay, the area border router. And then the area border router will find the path, using Dijkstra's algorithm again, to another area border router that is responsible for area 2. And then the packet is forwarded to the second area border router. And then this area border router will find an optimum path to the final destination, also using Dijkstra's algorithm. So Dijkstra is optimum in area 1, optimum in area 2, optimum in area 0, but there is no Dijkstra's algorithm running across areas. So what this does is that it achieves a compromise. The routers only have to send link state packets. They have to broadcast it periodically, but only within a smaller sized area, within area 1 or within area 2 or within area 0. So we don't have to broadcast link state announcements within the entire network. So if we have 100 routers, the 100 routers don't have to learn the routing tables of everyone. They only, for example, have to learn about the routing tables of only a subset, the 10 routers that are within its area, for example. So using this structure, OSPF is able to achieve a compromise. And obviously, a network administrator will have the flexibility to determine what is the size of the area and where are the borders of the area and so on. Okay. Now we can actually move on to the other topic, which is exterior gateway protocols. Now we have learned how a packet makes its way between any source and destination within the same autonomous system. What we want to learn now is how a packet jumps from one autonomous system to the next. We said that for this to happen, the border router at Autonomous System 1 will actually use an exterior gateway protocol called BGP to talk to another border router at Autonomous System 2 and then send the packet to it. We want to be able to understand this process in details in this lecture. And so what I will start with is a discussion that we have actually gone through earlier in the course, which is basically the structure of the Internet core itself. We said that the Internet core is made up of autonomous systems, but they are not all the same. They can actually be categorized into levels or tiers, where tier 3 is where we find our own autonomous system that we directly connect to, that we are subscribers of. Okay? In Egypt, they can be, for example, Orange DSL or Vodafone or Etisalat or any of these ISPs. Okay? How do these tier 3 ISPs get their own connectivity? They subscribe to a tier 2 ISP, and tier 2 ISP can also subscribe to a tier 1 ISP, and tier 1 ISP doesn't actually subscribe to anyone, but they create a peer-to-peer network among other tier 1 ISPs so that they can achieve global connectivity. In an abstract way, this structured Internet core looks like the figure that you see on the right. They're just a bunch of autonomous systems, regardless whether they are tier 1 or tier 2 or tier 3, and they are all inter-network. And so we want to be able to know how does BGP work between one border router in Autonomous System 1 and another border router in any other autonomous system. This is actually going to be our focus in this lecture. And in order to understand that, we have to be able to understand what does an autonomous system look like? What does an ISP look like? What is it made of? But before we understand what an ISP is made of, because this you can expect that it is a complicated networking structure, I will start with a similar system just to be able to then go to the structure of an ISP. We'll start by basically looking at what does a data center look like. If you don't know what a data center is, the data center is basically a networked system of devices that contains servers, switches, and different types of routers, all supporting the functionality of a certain organization. For example, the GUC has the data center. It has the intranet servers, and these servers are connected by switches, and then there are routers that connects the GUC network to the outside world. The GIU data center is the same. Okay. There are data centers, for example, in organizations. For example, let's say Facebook will have huge data centers across the world where you have the Facebook servers, and the Facebook servers are connected using switches and routers. So what does a data center typically look like? You can actually categorize it in levels. The very lowest level is where you find our end devices, typically the servers. And the servers are put in what we call a server rack, as we discussed before. So you will find, for example, one server here, and then all the servers are connected in the top layer using a switch. So all these servers here, for example, are connected using this switch. And quite often, you would have more than one switch connecting the same servers for redundancy, so that if one switch fails, another one can carry the traffic of the servers connected to it. If you have a very large number of servers, then it's likely that you will have several layers of switch hierarchy. So you have, for example, these switches here are then connected to switches at the upper level and so on. How many levels? That depends on the size of the network. This here is called the data center layer 2. Okay, it is where we find the switches, the switch racks, and we find the servers as well. Now, these switches are then networked. They are included in subnets, and they are networked using what is called an access router. Okay, so every group of switches are connected to an access router. The access router has a job of aggregating the traffic coming from all these servers and pass to the router through the switches and combining them into a traffic flow. And then the access router will determine where this traffic should go. If the destination is within the same data center, then it's going to choose which access router the traffic should be forwarded to. If the traffic is going outside of the data center, then it is going to be forwarded to the final layer, which is called the core router. The core router is basically the gateway of the data center to the outside world, the gateway to the internet. This is the one that will actually send the traffic outside and get the traffic coming from the internet back to the data center and then forward it to the appropriate access router. This is typically what a data center looks like. We divide it in terms of functionality, and once you divide it in terms of functionality, you can go and purchase the right equipment for the right layer. For example, access routers are required to support different networking services. They are required, for example, to support real-time applications. They are required to support something that is called virtual LANs, which we will see later in the course. They are required to actually support the networking functionality of layer 2. The core routers, they have different requirements. They are required to be very, very fast because they will actually carry the traffic of the entire data center. They are required to provide good transport services, so they have different requirements from the access routers. And there are basically different products in networking vendors like Cisco and Juniper and Brocade and all of those. There are different products suitable for whichever layer that you want to buy a router for. Okay. So this brings us to the discussion of what does an ISP look like. The ISP, you can actually think of it as a big data center. Okay. The ISP provides networking services to an entire country, for example. And so, again, it is actually categorized into levels. First of all, we divide the entire region that the ISP serves, let's say we divide the entire country, into what is called metropolitan areas or metros. These metros, we go and install the switching devices within the central offices. The metros can be, for example, the size of a city, or if you have a very big city, then it can be a part of the city. Now, within this part of the city, within this metro, you have many central offices, central basically. The ISPs will go and install their own switching devices, their own switches and routers at the central offices. Okay? And the central offices, they are already internet connected by optical fibers. This is actually part of the infrastructure. In Egypt, we are using DSL, which relies on the telephone network. In the telephone network, the central offices are already connected by optical fibers. This is what Telecom Egypt already has installed. And so the ISPs, they simply install switching devices at the central offices, and now they can actually send packets from one central office to the other. And this is exactly what happens. Within one metro, if the originating device or the sender is sending a packet to a receiver that is within the same metro, the packet will simply be routed within the switching devices in the central offices until it reaches the destination. If your packet is destined outside your metro, then it's going to go to a designated switching device, which is called a point of presence. Every metro will have a router that is called the point of presence. It is basically the border router, where if you want to send a packet outside the metro, you send it to this router. So each metro can then be categorized into 3 layers. The access layer, where you have the central office connection to the customer himself or herself. This is what we have at our homes. When you have a DSL connection, you connect your router to the telephone box, which is then connected to the central office. This is the bottom layer. And then you have the metro layer, where you have connections between COs, and then you have the core layers, where one metro is connected to another metro. Okay? There are different terminologies. For example, the router at the central office that you connect to directly is called the access router. And then the routers that connect the metros to each other are called border routers or backbone routers. The IETF has different terminology. For example, your equipment is called customer edge equipment. It is connected to a provider edge router, and then you have backbone routers that are called provider routers. They're just different terminologies for the same thing. Okay. And as in data centers, the routers have different functionality. So the access routers need to do aggregation. I will discuss aggregation in a little bit. It has to actually support customer services. The backbone routers, they provide high-speed interfaces and transport services. Okay, so once you reach a border router in an ISP, how does it actually go to another border router in another ISP? We said that we don't use interior gateway protocols because one ISP will be owned by one administrative entity and another ISP will be owned by a different administrative entity. And so, because you don't own the switching equipment at the other ISP, you cannot actually use an interior gateway protocol, because an interior gateway protocol would just simply find the best or the optimum path. In this case, only if everything is owned by the same administrative entity or the same autonomous system. But if we are jumping from one autonomous system to the other, we have to use an exterior gateway routing protocol, and there is actually only one running in the world, which is called BGP, or the Border Gateway Protocol. Okay. What is actually the job of the Border Gateway Protocol? Imagine that you have a device or a server in an autonomous system in Mexico wishing to send something to a server in an autonomous system in Australia. Now, the border router here will want to send the data to the border router in Australia. What they can do is that they can establish, let's say, a very long intercontinental fiber optic cable between Mexico and Australia across the ocean. Okay. This is not very practical, and even if they can do that, then they can just reach each other. If they want to actually communicate over the internet, more practically what they will be doing is that the border router will send packets from one autonomous system to the other until it reaches the destination. Now, BGP defines how one autonomous system reaches another autonomous system. How does the border router in Mexico know that to reach Australia, I actually have to send the packets through this border router? This is how BGP works. BGP works on the idea of announcements. Every router will announce what kinds of networks are connected to it. So the border router in Mexico will announce what are the subnets, what are the IP addresses that are connected to it. The border router in Australia will announce what are the subnets that are connected to it, and will announce these networks to the neighboring routers. Okay? And so the neighboring routers now know about these networks. If a packet comes that is destined to these networks, the routing table here is going to have an entry saying I should actually send it to Mexico. How would this routing entry be created? Based on an announcement that was made by the border router in Mexico. And by actually sending these announcements, the routing tables at different routers are built. Now, this is only for reachability. BGP can also enforce policies. So between Mexico and this other autonomous system, let's call it autonomous system X, they must have an agreement between them. They must have a contract saying, I'm going to send you the traffic for these networks, for example, and you send me the traffic for your networks as well. Okay? If they have this contractual agreement, then they can actually send each other traffic. If they don't have this contractual agreement, then there is no incentive for one autonomous system to send traffic to the other. And there has to be an incentive because these are all businesses. Just like the ISPs in Egypt, they are businesses. They are there only to make a profit. They are there to make money. So without an incentive, they do not actually need to send their traffic to each other. Okay. Now, before I explain how these announcements work and how BGP actually does this functionality, I will actually have to explain a very important concept in BGP and the networking in general, that is called route summarization. BGP is built on an idea of route summarization. Okay, what is actually route summarization? We said that every router will make an announcement that basically says what networks they are connected to it. So let's say in this figure you have router A. Router A is connected to these four networks. So router A should announce 200.199.48.0/24, .49.0/24, .50.0, and .51.0/24. These four networks should be announced by router A. And it is fine if router A makes these four individual announcements. But using route summarization, router A can actually make one announcement instead of four. How does this work? Let's take the first address, 200.199, and I'm going to convert 48 to binary. So it will be 00110000. So this here is 48, and then .0/24. Okay. The other one is 200.199.49, which is 00110001. This here is 49.0/24. The third one is 200.199.00110010, which is 50.0/24. 200.199.0011.0/24, and this is 51. I'm just converting these four fields to binary. Now, if you look at these four entries, 48, 49, 50, and 51, you will find that up to here, the bits are the same in all four addresses. The bits are 001100. These are the same in 48, 49, 50, and 51. Only the last two bits are different. So basically, instead of actually announcing four different subnets and they are all /24, router A can only announce one announcement, which is 200.199.48.0, but it is /22. Why /22? Because if you count the number of bits that are common among the four subnets, they will be 8 for 200, 8 for 199, so that's 16, and then 17, 18, 19, 20, 21, 22. So you have 22 bits that are common among all four addresses. All four subnets start with 200.199, so that's the first 16 bits common among the four subnets, and then 17, 18, 19, 20, 21, 22 bits are also common among four subnets. Only the 23rd and 24th bit, and possibly the ones after it, are different in the four subnets. So by announcing 200.199.48.0/22, I am actually announcing the four subnets. Any one of the four subnets will have the first 22 bits, 200.199.48.0. The first 22 bits will be the same. This is what this announcement means. So, how does this announcement summarize the addresses of the four subnets? Imagine what router Z will receive. It will receive only this announcement, 200.199.48.0/22. So it will create an entry in its routing table saying if the first 22 bits are 200.199.48.0, forward the packets to router A. This is what this announcement means. And from the point of view of router Z, it doesn't really care whether there are four subnets behind router A or two subnets or one subnet or whatever. Router Z will not care. Router Z will only care that this is actually the right destination. That in order to forward the packet to any of these four subnets, I just need to match with the first 22 bits. Now, if you remember our discussion of routing, we said that routers will forward packets based on something called the longest prefix match. When router Z receives a packet, it will examine the destination IP address. If it finds more than one entry, it will choose the entry that has the largest number of matches to that packet, to the destination IP address in that packet. And so if router Z gets an announcement 200.199.48.0/22 from router A, it will create an entry saying, if the first 22 bits of the destination IP address matches that, just send the packets to router. Same thing, router C will do the same thing. So at the end of the day, you see that router B only sends one announcement where it summarizes the 4 subnets into just one announcement, and router C will also send one announcement summarizing the 3 subnets that it has. You will notice here that the announcement from router C is only /21, while the announcements in router A and B are /22. Why is that? It's just because of the IP addresses and the subnets. You will see that the subnets in router A and router B are contiguous blocks, meaning that they are complete blocks. They follow each other. So 48, the last 2 bits in 48 are 00. 49, the last 2 bits are 01. 50, the last 2 bits are 10. 51, the last 2 bits are 11. Okay? But if you look at the subnets in router C, they are .56 and .57, and then you have .63. .63 is not a contiguous block. There is a difference in the bits between 56 and 57. And so if you convert those to binary, you will find that the only common bits between the 3 addresses are only actually the first 21 bits. This is why we summarize as /21. It doesn't actually matter whether you summarize as /21 or /22. You just find what are the common bits between all the subnets that are connected to the router, and these become the announcement. Now, router Z will receive the 3 announcements from routers A, B, and C, and it will also announce everything to the outside world. Now, router Z can do the same, can announce 3 different announcements, which are 200.199.48.0/22, .52.0/22, and .56.0/21. Okay. However, if you convert 200.199, then we convert .52, which is 00110100. This is 52, and then .56, that is 200.199.0011100, and then we have the first address, which is this is 56. 200.199.0011000. This is 48. Okay. If you take a look at these 3 addresses, you will find that the only common bits are up to here. After that, there are differences between the 3 announcements. So what you can do is you can just count 8, 16, 17, 18, 19, 20. And then the summarization of these 3 announcements is 200.199.48.0/20. This is what router Z actually announces to the outside world. So the outside world, if they receive a packet where the first 20 bits are 200.199.48.0, they will just send it to router Z. Now you will notice here that 200.199.48.0 appeared in the announcement of router Z, appeared in the announcement of router A, and appeared in the subnet connected to router A. However, each one of those had a different subnet mask. The subnet behind router A was /24. The announcement by router A was /22. The announcement by router Z was /20. Okay? So even though it is the same address, 200.199.48.0, but the subnet mask creates a big difference. It tells the other routers how many bits it needs to match. And so if it's .48.0 but it's /20, only the first 20 bits will have to match. This is basically what BGP announces. They do route summarization so that they actually only announce smaller number of announcements rather than announcing every single subnet, and also to save the spaces in the routing tables of the routers as well. Okay. So the routers that use BGP will announce the networks that are connected to them. What would the other routers do? So the border router in this autonomous system, autonomous system 1, will announce to the border router in autonomous system 2 that any address with prefix P is connected to me. Any address where the first number of bits are so and so are actually connected to me. Now, the border router rejecting. What does it mean to accept or reject? If AS2 accepts this announcement, then it acknowledges that if it has traffic, it will send it to autonomous system 1. If it has traffic with this IP address, or the first few bits of the IP address matches this announcement, it will send it to autonomous system 1. Okay? This means that autonomous system 2 now knows how to forward packets to the networks connected to autonomous system 1. The opposite has not yet been achieved, meaning that autonomous system 1 has not yet learned how to forward packets to the networks connected in autonomous system 2. How will autonomous system 1 learn? Through an announcement made by autonomous system 2. So autonomous system 2 has to also announce its networks to the neighboring autonomous systems, autonomous system 1 in this case. And autonomous system 1 has the option either to accept or reject. If autonomous system 1 accepts the announcements of autonomous system 2, then when it receives a packet destined to a network in autonomous system 2, it will send the packet to it. Okay, this is what the announcement actually means. Every autonomous system has the freedom to accept or reject announcements, and BGP will enforce these policies. If an autonomous system does not want to accept an announcement from another autonomous system, then BGP will reject all the packets coming from that autonomous system. Okay? You will notice here that the flow of traffic is in the opposite direction to the announcements. So if the announcement is sent from autonomous system 1 to autonomous system 2, this announcement will identify how traffic will flow from autonomous system 2 to autonomous system 1. I will repeat that. The announcement from autonomous system 1 to autonomous system 2 identifies how traffic will flow from autonomous system 2 to autonomous system 1, meaning that the flow of the announcement is in the opposite direction to the flow of the actual traffic. Same thing for the announcement from autonomous system 2. The announcement of autonomous system 2 to autonomous system 1 specifies how the traffic will flow from autonomous system 1 to autonomous system 2. The packet flow, the actual data flow, is in the opposite direction of the flow of the announcements themselves. Okay, and this brings us to the next topic, which is how does an autonomous system control the traffic that is coming to it and control the traffic that is coming out of it. And by control the traffic, meaning how to receive packets and how to send packets. We can actually divide the traffic into ingress traffic and egress traffic. Ingress traffic is the traffic coming to the autonomous system, so the destination is a network within the autonomous system, and egress traffic is the traffic that these networks are sending outside of the autonomous system. So the ingress traffic is how packets get to your network and your customer's network. So if you are forwarding actually traffic to another autonomous system here, this is also ingress traffic. Once you forward it, it becomes egress traffic. Okay? So ingress traffic, what does it depend on? If the traffic is coming to you, then the traffic that is coming to you will be based on announcements that you have made. Remember from the slide, the traffic that is coming to you is in the opposite direction of the announcements that you make. So the ingress traffic, which is traffic that is coming to you, is based on announcements that you make to the outside world. And so, what traffic gets sent to you? Well, that would depend on what you insert in these announcements. What are you announcing? What kind of addresses are you announcing? Whatever you announce, you will get the traffic for it. So if you announce the IP address of another autonomous system, if this is X and this is Y, and you announce Y to the rest of the world, even though it is not directly connected to you, you will get actually the traffic of Y. So every autonomous system needs to be very careful as to what it announces, because if it announces an address, it will get the traffic for that address. Okay? This is ingress traffic. So every autonomous system controls what it receives based on what it announces. This is the easy part, because every autonomous system will actually have control over what it actually announces to the world. They are actually free to announce whatever they want. The more difficult one is the egress traffic, the traffic that is going out, the traffic that my customers send to the rest of the world. This is actually based on the announcements that other autonomous systems make. And what do I do with these announcements? Do I accept these announcements? Do I reject them? Okay. I cannot actually control the announcements made by other autonomous systems. So autonomous system X cannot control the announcements made by autonomous system Y, which means that I don't have full control over how the traffic will leave my network. I don't have full control over how the traffic will be sent over the internet. Okay? Which is why every autonomous system needs to make agreements, as we will see in a little bit. These agreements with other autonomous systems, will actually allow there to exist a policy between autonomous systems over how to send traffic. Receiving traffic is easy, the ingress traffic is easy because I can actually control it based on what I announce. But sending traffic is difficult because it depends on what the others will announce to me and whether I will accept them or not and whether I will have an agreement with them or not. Okay? So, in order for the devices or the routers to be able to control what happens to the egress traffic, the BGP protocol has to enforce routing policies. This routing policies allows the routers to make decisions over each packet, whether to accept or reject an announcement based on an individual route, or whether it's a route that is originating at a specific autonomous system. Let's say, for example, the US does not want actually their traffic to go over any route in China. So they don't actually want to accept any announcements made there, okay? Or maybe they don't have an agreement with some autonomous systems in Russia or any other place, so they don't actually want their traffic to be sent there. Whatever the routing policy of an autonomous system, they can actually enforce it by accepting and rejecting announcements from other autonomous systems. Now, every autonomous system will now have a dilemma as to what kind of policies or what kind of announcements it accepts or rejects. Let's say you have autonomous system X and autonomous system Y. Autonomous system X has some customers. They are actually subscribers of ISPX, and autonomous system Y also has some customers. They are the subscribers of autonomous system Y. Now, obviously, these subscribers might want to send data to each other. So what they will do is that they will send the traffic through X, and they will rely that X will find a way somehow to reach the subscribers of Y. The problem is X is a business. So to make more profit, X would want the subscribers of Y to switch to it. Why would a subscriber in autonomous system Y switch to X? They will do that only if X provides a better service. If it's cheaper, for example, or if it has better connectivity. So if X prevents the subscribers of Y from sending data to it, the subscribers of Y might actually find themselves not having connectivity to the subscribers of X in this case. The problem is, autonomous system Y will probably do the same. They will prevent the subscribers of X from sending data to it. And so now there is a dilemma. X would like actually to attract the subscribers of Y, and Y would like to attract the subscribers of X. So they have an incentive to deny connectivity to the subscribers of Y, or to deny connectivity to the subscribers of the other ISP or the other AS. However, my own subscribers would also like connectivity to other autonomous systems. They subscribe to me in order to have such connectivity. Okay? And so I also have an incentive to provide some kind of agreement with Y so that we can actually exchange traffic with each other. This is actually the dilemma. Every ISP would like to attract more customers, and these customers might actually be served by other ISPs, but in order to have global connectivity, the ISPs or the autonomous systems need to cooperate. They need to cooperate. They need to have agreements so that they can actually have such global connectivities. This is the incentive for one autonomous system to cooperate with another one. Without this fact, there would not be global connectivity among autonomous systems at all. Okay. So once they have an agreement, they have a routing policy, and they can now actually start enforcing this routing policy. Now let's see the limitations. Let's see actually the difficulty of having a routing policy across all the autonomous systems in the world. Let's say you have autonomous system 99 that is sending packets to two autonomous systems, the red and the green autonomous systems. Now, how does autonomous system 99 know how to reach the red and the green ones? This is because in order for AS99 to send data packets to red and green must have made announcements before. And these announcements eventually will reach AS99. And so AS99 has the freedom to accept the routes or accept the announcements made by the red ASP on the red link, and has the freedom to accept the announcements made by the green ISP on the green link. Okay? Let's say that this is actually the desired behavior. AS99 wants to use the red link for the red AS and wants to use the green link for the green AS. So it can simply accept the announcements made by the red AS on the red link and the green AS on the green link. Even there may be a different path through the internet. So the red AS may be accessible through the green link, and the green AS might be accessible through the red link. But AS99 has the freedom to send packets to the red and green AS by accepting announcements from them on specific links. Okay? The opposite is not so easy. So if the red and green AS are actually now sending traffic to AS99, that means AS99 must have made an announcement to the red and green AS. The problem is, if in this case AS99 would like to receive the red traffic on the red link and green traffic on the green link, this is not possible unless AS22 cooperates. It is not possible unless AS22 will actually send the traffic over the red and green links as per the desires of AS99. Without such an agreement between AS99 and AS22, the AS22 is actually free to send the traffic over any of those links. And AS99 would not actually be able to object, because if it objects, it will not receive the traffic at all. So the customers of AS99 in this case will be disappointed because they didn't receive the traffic from the red and green AS. Okay? So controlling that part, controlling what is coming to AS99 is a little bit challenging because it requires actually the cooperation of other autonomous systems. So every communication, whether it's ingress or egress, will have its limitations. AS99 will control its announcements, so it will control actually what it announces to AS22, but if it has more than one link to AS22, it cannot actually force AS22 to send particular traffic over particular links unless it has a predefined agreement with them. Okay. Okay. Let's take some examples just to actually see how this is done. Let's say there are 6 autonomous systems, 6 ISPs. ISP A and B are in tier 3, meaning that they are the ones that have direct connections to customers. You have ISP C and D, which are in tier 2, meaning that their customers are other ISPs in tier 3. And you have the highest tier 1 where you find ISP E and F, which are basically responsible for intercontinental links. Now, there are several things that can happen. First of all, there can be a relationship between ISP A and ISP C, where ISP A wants actually the customers of it to be announced. So basically, ISP A has some customers, and these customers want to receive data. And so how do other networks know that there are customers of ISP A? Because ISP A will actually announce the networks of itself to the provider, which is ISPC in this case. So ISPA will say these are the networks that are reachable through me by using route summarization as we discussed. And so ISPC will know that there are networks announced by A, okay, that are reachable through this link. And if ISPC accepts this announcement, then it can actually start forwarding data in the opposite direction, as we said, to ISPA. Okay. Same thing can happen between ISPC and ISPD. Now, ISPC can say, these are the networks that are connected directly to me. So if ISPC also has some customers, these customers can be other autonomous systems, for example. Let's say this is another autonomous system G, for example. It can say, these are the networks of ISPC, the networks that are my own customers, and these are also the networks of ISPA that are reachable through ISPC. So these two networks are announced to ISPD, either separately or through route summarization, if they can be summarized. And so any traffic that ISPD receives that is going either to the customers of ISPC or to the customers of ISPA will be sent to ISPC in this case. Now, ISPC can make the exact same announcement to a tier 1 provider, which is ISPE, so that if ISPE also receives any traffic that is going to the customers of ISPC or the customers of ISPA, can actually be reachable through ISPC in this case. So now, anything that is behind ISPD will know how to reach ISPC and A, and anything connected to ISPE will know also how to reach the customers of ISPC and A. Okay. If ISPC makes these two announcements to ISPD, ISPD actually has the freedom to accept or reject all or part of it. For example, ISPD can tell you, I'm not actually going to accept the networks at A. I'm not going to forward to you through this link the traffic going to the networks at A. And so in this case, if ISPD receives the packet that is going to ISPA, it will not actually forward it to ISPC. So ISPC in this case will have to rely on the tier 1 provider to forward the packets of network A. But however, in this case, if ISPD receives packets that are going to the customers of ISPC, they can actually be forwarded in the reverse direction. Which one to be accepted and which one to be rejected? Well, this would depend on the kind of agreement that these two ISPs would have with each other beforehand. They have to have an agreement beforehand which traffic will be forwarded, and based on this agreement, the ISPs can enforce whatever contract they have with each other. Between the two ISPs, there can also be an agreement. Each one will announce to the other, here is actually the networks that are reachable through me, and they announce to each other if they both accept. And again, the acceptance has to be based on an agreement between the two. They can actually start forwarding data to each other. And in all cases, the networks will actually do route summarization in order to announce. So at the end of the day, it may not be the case that they're announcing 10 different network addresses. It can be just a few based on how many network addresses can actually be summarized in this case. And so if, let's say we want actually to see how a packet from ISPA, let's say there is a customer here. Okay, there's a customer here wishing actually to send data to a customer of ISPB. So the packet should go from ISPA to ISPB. How does this travel? ISPA will make an announcement, or would have made an announcement of the networks connected to ISPA to ISPC. Now, the packet, if this announcement goes, then the packets going to ISPA will actually be sent by ISPC. Now let's see what happens if ISPA wants to send something to ISPD, meaning that this is egress traffic. This is traffic that is going outside ISPA. Okay? So for this to happen, ISPB should announce its reachability. So ISPB should announce, should make an announcement to the networks connected to it, to ISPD. ISPD should include this network address in the announcement that it sends to ISPF, and ISPF should make the announcement to ISPE, should make the announcement to ISPC, and then should make the announcement to ISPA. Now, ISPA now knows that in order to send actually traffic to ISPB, the traffic should actually go to ISPC, and then ISPC knows that the traffic should go to ISPE, then here, then here, and then here. If ISPD makes this announcement directly to ISPC, in this case, there would be an agreement between ISPC and ISPD to send each other's traffic. If there is some kind of agreement between ISP A and B, then there would be an announcement from B to A directly, and in this case, the data can actually be sent directly from ISP A to ISP B without actually going through the other parts of the hierarchy. Where does the traffic flow? It's based on who made which announcement and who hears this announcement and accepts it and adds it to their routing table. This is basically how BGP works. Now let's see, for the remaining part of this lecture, we want to see why someone would make such an announcement, why someone should actually accept this announcement. First of all, there is a dilemma that we started discussing actually last time, which is basically that every ISP wants to attract as many customers as it can. An ISP is a business. It sells internet connectivity to customers. And so an ISP typically has some customers. Okay, let's say we have ISP X, it has some customers, and it wants to attract the customers of other ISPs. So let's say in this case, we have ISP Y, it also has some customers. So obviously ISP X wants to attract more customers from its competitor, which is ISP Y. And so what would make someone choose one ISP over the other? Obviously their connectivity prices plays a role, but also if there are reachability issues, then this would also play a role. Let's say ISPX has been more successful at establishing agreements with other ISPs to exchange traffic, meaning that ISPX has better reachability. It has shorter paths to other ISPs. So in this case, ISPX would have shorter delays in sending and receiving traffic because it has other agreements with other ISPs. So ISPX in this case would be popular, would be attractive to other people because other people will think that it is a faster ISP. It has actually better deals with other autonomous systems, and so it can send and receive data faster, and so it will be the more popular one. ISP Y wouldn't then want to make an agreement with ISP X to send and receive data through it because ISP X has actually better reachability. Now here is the dilemma. ISP X has the incentive to deny such an agreement to ISP Y so that the customers of Y will think that ISP X is better, will think that it's faster. However, the customers of X want to exchange data with the customers of Y. So then also X has another incentive on the opposite side to make an agreement with Y. This is the dilemma. On one side, X has the incentive to deny Y an agreement in order to deny the customers of Y the chance to send and receive data. And on the other side, X has another incentive to actually send and receive data with Y so that the customers of X can actually communicate with the customers of Y. At the end of the day, you as a customer, you don't care what kind of profit your ISP makes. You just care about your own connectivity. You care about the speed of your connectivity. This is actually what you want from your ISP, okay? There are also some limitations on every ISP on how to send and receive data. We said that in order to actually communicate with a certain autonomous system, you actually have the freedom as an autonomous system to accept routes in whatever way you want, according to any policy you want. Also, there are limitations on how the data is forwarded. Let's say there are two ISPs, the red and green one. They are reachable through several paths over the internet, okay? And so autonomous system 99 can reach the red and green autonomous systems through several paths. Let's say autonomous system 99 wants to use this link to reach the red autonomous system and wants to use this link to reach the green autonomous system. This is relatively easy because the red and green autonomous systems will actually make announcements to reach their networks, the networks that are behind red and green. Okay, they will make these announcements, and these announcements may reach Autonomous System 99 through several ways. For example, AS99 may actually receive the announcement for red and green from the two links. Now, Autonomous System 99 can accept the red announcement over the green link, in which case the red traffic will be sent over the red link and the green traffic will be sent over the green link, enforcing the policy that Autonomous System 99 would like to enforce. How did Autonomous System 99 enforce this policy? Because it accepted the announcement from red and green on the link that it chose. So if Autonomous System 99 receives the announcement for the same network over several links, then it can choose where to accept the announcement. If it receives the announcement for red or green or both over a single link only, then it will have no choice. If it wants to reach this network, it will have to accept it over the link on which the announcement it was received. So there is some flexibility there. Let's see the opposite scenario where Autonomous System 99 is receiving data from red and green. And it is receiving data from red and green through Autonomous System 22. Both traffic from red and green will somehow reach Autonomous System 22 and will actually send it to Autonomous System 99. Now, in order for Autonomous System 99 to receive traffic, it would have to make the announcement of its own network. It will have to make this announcement over all its links, over the red and green. This is actually how red and green will know that if there are packets going to Autonomous System 99 to send it to Autonomous System 22. But how would Autonomous System 99 in this case enforce that the red traffic goes over the red link and the green traffic goes over the green link? By itself, Autonomous System 99 would have no control over that because it would depend on what Autonomous System 22 accepts. If Autonomous System 22 accepts that the red traffic will be forwarded over the red link and the green traffic will be forwarded over the green link, then this will be successful. If Autonomous System 22 doesn't care, then Autonomous System 99 has no way of enforcing how the traffic is received. And so we have now several things that we discussed. We have plain reachability information, what network, what autonomous system sees. Okay, this is just based on announcement. We have also how to forward traffic, which is the scenario that we're discussing here. How to send traffic is relatively straightforward because it's based on how you accept these announcements. How to receive traffic is more challenging because it depends on how other autonomous systems handle your traffic, the traffic that they are sending to you. These are all policy limitations that serve as a motivation or incentive for autonomous systems to have dealings or contracts with each other. Okay. Now, the Border Gateway Protocol is the way to enforce these policies. And it works by establishing a TCP connection with a router. So in these two autonomous systems, there will be a border router here and a border router there. And all BGP policies will actually be enforced by establishing a TCP connection over the border routers. And the TCP connection has to stay established all the time as long as these two routers are in contact with each other. In the context of autonomous systems and border routers, these TCP connections are over all the time. They are actually established all the time. It's not like when you establish a TCP connection with a server, for example, where you just establish a TCP connection, you send an HTTP request and receive a response, and then you terminate the HTTP connection when you no longer need it. In this case, the TCP connection, in case of BGP, the TCP connection will be established all the time. And in fact, every 60 seconds or so, the routers will send actually a keep alive message to each other saying that I'm still here, basically. Okay. And the policies of BGP, they have to be manually configured, meaning that there is a network administrator that will actually sit at the router and configure it either locally or remotely, telling this router what to accept and what to reject, what to send and what to receive. After this configuration is done, BGP will enforce this policy. Okay. This, what we have been discussing so far, is the version of BGP that is called external BGP. This is the default version, and this is the one that is used between autonomous systems. In very large networks, very large data centers, there is also another version of BGP that can run internally. This is called iBGP or internal BGP. So let me just explain using this scenario. Let's say you have these two autonomous systems, each one having and going to a customer at autonomous system. Let's say this is autonomous system 2. This is autonomous system 1. Let's say there is a customer of autonomous system 1 wanting to send traffic to autonomous system 2. Now, the packet is received at border router A, and border router A has to send it to border router B, and then there is going to be eBGP that is running here so that border router B can send it to border router C at autonomous system 2, and then border router C will send it to border router D, which then will send it to the customer. eBGP, the external version of BGP, will be running only between routers B and C. Now, how does border router A identify that it is border router B that needs to receive this traffic? This is where the internal version of BGP will run. Okay? It runs to identify the exits. It runs to identify where is the border router that needs to receive this data. So router A can actually run iBGP with router B to identify that if the packet is going to D, A must actually send it to B. Okay. Now, once the iBGP identifies that B is the exit, an internal gateway protocol like OSPF, for example, can actually be used to forward the packets all the way to B. Okay. And then the external version of BGP will run so that the packets are sent from B to C, and then iBGP will be established between routers C and D so that C identifies that D is the exit router that needs to get the traffic, and then OSPF, for example, or another internal gateway protocol will forward the packets to router D, which will forward them to the destination. So you have the external and internal versions. The external version is when the packet needs to jump from one autonomous system to the other. The internal version is used in large networks where you have many possible exits, many possible border routers, and you need to identify which one. The two versions of the protocol have some differences. First of all, we said that in order for BGP to work, the routers actually have to establish a TCP connection between them. In eBGP, the TCP connection is actually established over a physical link, meaning that the TCP connection, which is the logical connection, is over the same physical connection. The endpoints of TCP, in this case, are R1 and R2. Okay? Unlike, for example, what you would have at your device, if this is the client and this is the server, the TCP connection will be between the client and the server, and then the physical connection can actually run over several routers. Okay? In BGP, there cannot be any intermediate devices between the endpoints of the TCP connection, meaning that there cannot be any routers between R1 and R2. TCP is over the same physical connection between R1 and R2. Okay. In iBGP, the internal version, this is not the case. If you have an iBGP connection between R1 and R2, it can be over the physical connection between R1 and R2, or it can be through R3. This is fine in iBGP. There can be intermediate routers between the two endpoints of the iBGP connection. Okay. This is something that we have discussed. How does actually routing information get accumulated? For example, how does AS500 learn how to reach AS100? AS100 will actually make an announcement that includes 180.10.0.0/16 to AS200. AS200 will then include this announcement. It will include AS100 in its announcement to AS300. And then AS300 will include the announcements of both 200 and 100 in its announcement to 500. And so AS500 will learn that to reach 180.10.0.0, these are the autonomous systems where the packet should jump. Okay. Now, what we will discuss is actually the types of relationships that autonomous systems have with each other. Now we have discussed why autonomous systems actually make announcements, what incentivizes them or what motivates them to make an announcement. And we discussed also how autonomous systems have some freedom of controlling where the traffic is sent. Now we will discuss the types of relationships or the types of agreements that autonomous systems have with each other. Okay. The first type of relationship is called customer-provider relationship. This is where a small autonomous system buys connectivity from a bigger one. Tier 3 buying a connectivity from Tier 2. So here, for example, we have autonomous systems such as C1, C2, and C3. These are, let's say, Tier 3. Okay. They want to have internet connectivity, so they buy internet connectivity from ISPX, which is, let's say, a Tier 2 autonomous system. So they buy connectivity means that they actually pay money. Okay, they pay money to ISPX. Why? So that if there is traffic actually going to C1, C2, or C3, ISPX will forward this traffic to C1, C2, or C3. So now when C1, C2, and C3 will make the announcement of their own networks to ISPX, ISPX would now accept it. Why? Because they have paid money. ISPX will not accept these announcements unless C1 and C2 and C3 will actually pay the money. Okay, this is called a transit agreement. A transit agreement involves one party paying money to the other party to accept its announcements. Okay, and this agreement will include, for example, a certain amount of data. Let's say you cannot send me more than 100 terabytes of data per month or per week or per whatever. Okay, then BGP will also enforce that once this data is exceeded, I will no longer send anything to you as per our agreement. This is the first type of agreement. And when Tier 3 wants to make this agreement or the transit agreement with Tier 2, it involves money. When Tier 2 wants to make this agreement with ISPP, which is Tier 1, it involves actually a larger amount of money. So every step up the hierarchy involves actually more money being paid. So when Tier 2 wants to be a customer of Tier 1, it also has to pay money. Why? Because Tier 2 will typically receive much more data from Tier 1 than Tier 3 would receive from Tier 2. Whenever you go up the hierarchy, we involve actually a larger amount or a larger volume of traffic. Okay. This is the first type of agreement. It's a customer-provider agreement or what is called a transit agreement. The other type of agreement is called peer-to-peer. This is when one ISP makes a peering agreement with another ISP, typically at the same level. So if we have ISP Z, X, and Y, all of them are at tier 2. Okay, they can make a peering agreement with each other, saying that if you receive my traffic, send it to me, and if I receive your traffic, I will send to you. Typically, peering agreement does not involve financial settlements, meaning that they don't pay anything to each other. They just have an agreement to accept each other's announcements. What would motivate these ISPs to have such an agreement with each other? If they see that there is actually a large volume of traffic that is sent through each other. So if Z and X see that there are actually customers of Z receiving data from X and there are customers of X receiving data from Z, they have an incentive to make a peering agreement with each other. And by the way, the volume of traffic sent from and to Z and X doesn't have to be fully symmetric, meaning that there can actually be asymmetric connectivity, meaning that, for example, X can be receiving more data from Z than Z is receiving from X. They can still actually have a peering agreement. The peering agreement would not make sense if and only if the traffic is highly asymmetric, meaning that one party receives much more traffic from the other one in this case. And so in this case, it would make sense to have a transit agreement than a peering agreement. Peering agreement is established when the volume of traffic sent to and from the ISPs are more or less similar. Okay, and typically peering agreements happen at ISPs of the same level. So tier 2 and tier 2, tier 1 and tier 1, or tier 3 and tier 3 in this case. Okay. By the way, if you want to Google something, this is just for your own knowledge, there is something called an Internet Exchange Point. This is an organization that allows autonomous systems to have a peering agreement. So I want you to go to a website of something called the Cairo Internet Exchange Point or the Cairo IXP. Google that and you will find its website. You will actually see the ISPs in Egypt having peering agreements with each other. You can see actually what is the network topology that they have in this case. Okay. So when do ISPs actually make an announcement? When they stand to make money out of it. When do they make a transit agreement or a peering agreement? When there is profit to be had, either directly or indirectly. They would make a peering agreement when they see that there is a larger volume of traffic going from another ISP. They would make a transit agreement if they see that they actually need the service of this other ISP and they actually have to pay money for it in this case. Okay. So we have now discussed more or less the features of BGP. If, by the way, if one autonomous system finds that there is more than one possible path to a destination, there are actually possibilities in BGP to choose one based on attributes, to choose one, for example, based on the shortest path or on delay or something like that. However, policy comes first. So there has to be policy or agreements between autonomous systems first, and then if there is more than one possibility, then they can actually choose the best one. For the remaining part of this lecture, I will actually be discussing some security features or some security vulnerabilities that are associated with BGP. One of the main sources of BGP insecurities is that it is manually configured. The routers are manually configured. BGP, as we said, enforces policy. And so this is not something that the routers can figure out dynamically. It's not like internal gateway protocols like OSPF, where the job of the routing protocol is simply to find the best path. Because there are policies and there is money and there are agreements actually between the routers, then it has to be manually configured. So this actually produces several vulnerabilities. And because this is also based on TCP, it opens it to several types of attacks. I will not actually go into the details of the TCP attacks now, but I will actually be discussing in details the problems that occur with manual configuration. And to understand that, I will actually show you some examples from the internet history to see what happens due to manual configuration faults. One of the most well-known examples is the issue that happened in Pakistan, and I think it was 2008. Basically, Pakistan Telecom wanted to ban YouTube. It was a government decision, and it wanted to ban YouTube in the country. And so Pakistan had several internet service providers. One is called Telnor, one is called Aga Khan, one is called Multinet. And obviously the customers of these three ISPs were receiving YouTube connectivity. And these autonomous systems may actually have connections to YouTube outside the telecom connections of the Pakistan Telecom. Okay, so how would the Pakistani telecom, the government telecom, be able to control how the traffic from these three autonomous systems or these three ISPs to YouTube? Basically, the idea was YouTube announces its own connectivity. So let's say this is the autonomous system that is responsible for YouTube. It announces its connectivity. And whenever one of these three autonomous systems want to receive or send traffic to YouTube, send an HTTP request to YouTube, they will find the shortest path, which is typically through the Pakistani telecom. Okay, and so the Pakistani telecom wanted to make sure that it announces the shortest path to YouTube to make sure that these three autonomous systems will send all the traffic to YouTube. And so the best way is that the Pakistani telecom would make an announcement that includes the YouTube address to the three autonomous systems so that they can send the traffic to it. And then the Pakistani telecom can actually just drop the HTTP requests that are going to YouTube. And so nothing will make it out of the Pakistani telecom. Okay. Now the problem is a manual configuration caused that the Pakistani telecom announced the YouTube network. So YouTube network also makes the announcement, and now the three autonomous systems have two possible ways to YouTube, one through the external network and one through the Pakistani telecom. Not only that, other autonomous systems now hear this announcement, and now everyone will be sending YouTube traffic to the Pakistani telecom. This caused a huge flow of traffic that is originally going to YouTube to the Pakistani telecom, and the Pakistani telecom failed, and the network of the entire country crashed. Okay, it was over flooded with HTTP requests that are originally going to YouTube, and the network failed. What they should have done is that they should have made this announcement only internally, only to the internal routers of the 3 ISPs within the country. What happened was that they made this announcement everywhere, even at the routers going to the internet. So obviously, other routers heard this announcement and they thought that there is a better path to YouTube through the Pakistani telecom, and they started sending YouTube traffic to it. And YouTube traffic is obviously huge, and so the network failed. Okay. The other example was actually not of a fault, but it was a suspicious interception of traffic by the Chinese telecom. Okay. There was an autonomous system that is in the US that is connected to the ISP known as Verizon Wireless, and the traffic basically should flow through Verizon Wireless, and there is another autonomous system that is called Level 3. And so basically, the announcement is made here to Verizon Wireless, which forwards it to Level 3. And now, if ISP1 has traffic that is going to 22394, it will send actually this traffic through this path. Okay. What China Telecom did is that it also announced the same ISP. It made this announcement, and now ISP1, once it has traffic to send to this network, it has two possibilities. One that goes through Level 3, and then through Verizon, and then through 22394, and one that goes directly through Chinatel. You have to take care here that Chinatel appeared to have this network 66.174.161.0 internally. It's as if China Telecom has purchased this network. And so ISP1 now thinks that this network is directly connected to Chinatel, and so it will send the packets to it. Now, what happened in reality is that this was an interception of traffic. China Telecom received the traffic from all over the world and then forwarded it secretly to 22394. Okay, so that 22394, it actually took a while until they discovered that the packets are actually going through China Telecom in this case. Okay. The third example was related to Bitcoin. It was a Bitcoin hijack that occurred in Canada in 2014. To understand how this hijack works, I just give you a little bit of background about how cryptocurrency and how Bitcoin works. Bitcoin and other cryptocurrencies are based on something called a blockchain. A blockchain is basically just a data structure. A blockchain consists of blocks where every block contains a group of transactions. Okay, and the blocks are linked so that it becomes impossible for an attacker to change the quantities of the transactions in one block. Okay, the link between the blocks in the blockchain are based on cryptography algorithms that we will actually learn later in our curriculum. But for now, just actually know that there are blocks in a blockchain that keep the transaction secret. How does one block get produced? It gets produced in actually a peer-to-peer network, okay, that is a global network, peer-to-peer, okay? A global network that is a peer-to-peer network of what are called miners. The miners use their computational power in order to produce one block. They gather the transactions from all over the world and they put a group of transactions and produce a block. And they have to solve a cryptographic puzzle before producing the block, and the cryptographic puzzle is difficult to actually solve. And so there are miners that dedicate their computing power to solve the puzzle, and the miners collaborate together. So every group of miners will actually collaborate together to produce a block, to use their computational power to produce a block. And once a miner produces a block, they will get Bitcoin as a reward. No. So now, how did the attack works? How did the attack work? Basically, what will happen is that there is a mining pool server where the miners will actually send the traffic to it, will send the solutions of the cryptographic puzzle to it in order to contribute to solving the puzzle and producing a block, and so getting a reward. And so obviously, because this is the internet, this works using BGP announcements. So in order for the miner to reach the pool, the mining pool server, there would be announcements that determine how the traffic should flow. Basically, this should be the real flow of the traffic. What the attacker did is that the attacker actually announced the address of the legitimate mining server. And so the victim, the miners in this case, rather than actually sending the traffic to the legitimate mining pool server, they will sending the solutions of their puzzles to the attacker. And so the attacker would actually be getting the solutions of the puzzles and getting the reward instead of the miners in the legitimate mining pool. And there was actually a very large amount of bitcoins that were hijacked in this process. Okay. Now, how to secure BGP from such attacks? There are several solutions. The first solution that we will discuss is using something called a digital signature, which is in an infrastructure called public key infrastructure. Basically, every autonomous system, when it is sending the announcement, it signs it, just like when you would actually sign an application to make sure that it is authenticated. So if we take this example, we said that China Telecom was able to hijack the traffic of 66.174.161.0 because it announced its IP address. Okay, it announced its network address, as if this network is now connected internally to China Telecom. With RPKI, with the public key infrastructure, basically what will happen is 22394 will digitally sign the announcement. Okay, so it will say that I am actually announcing 66.174.161.0, and here is my signature to validate that this network is connected internally to me. So in this case, China Telecom would not actually be able to produce the same announcement. It cannot send the announcement that this network is connected internally to China Telecom because it doesn't have the signature. And the signature, for your information, is based on cryptographic algorithms that are computationally very difficult to fake. So no one can actually produce the same signature as 22394. Every autonomous system will have a unique signature that cannot be faked, cannot be manipulated. Okay, and so China Telecom in this case cannot pretend to be 22394, cannot pretend that it owns 66.174.161.0. However, this still doesn't solve the problem fully, because although China Telecom cannot announce this address as if it's an internal network, it can simply announce that it has a route to this network. So it will say, I actually have a route to 66.174.61.0, and it is through 22394. So the announcement will still carry the digital signature of 22394, but now China Telecom will simply say, well, I have a better path than level 3. Level 3 is actually sending to level 3 and then Verizon Wireless and then to 22394. China Telecom will simply say, well, I have a better path. Even though the digital signature is valid, other autonomous systems will actually not be able to know that this is the shorter path, and so can actually send the packet still to China Telecom. The solution lies in what is called root attestation. Basically, then we will have to validate every path. This is in a protocol that is called the Secure Origin BGP or SBGP. Okay, you have to have root attestation. Basically, not just actually including the digital signature of the autonomous system that is announcing the address, but also including this digital signature over the entire path. So when 22394 makes the announcement, it will include its digital signature and will say, I am actually announcing this network to Verizon Wireless. It's not just that I'm just announcing this network address, I will include also the address of the destination in my digital signature. So the announcement is only valid to Verizon Wireless. Okay, and then when Verizon Wireless makes its announcement, it will say, I have actually an announcement that is from 22394, and the announcement is to Verizon Wireless, meaning that I am actually the destination of this announcement. And then level 3 would do the same. It will include the announcement from 22394, which is to Verizon Wireless, and will include the announcement from Verizon Wireless. And so China Telecom in this case cannot hijack this traffic because if it hijacks the traffic, it will include level 3, and the announcement from Verizon Wireless. Every announcement includes its destination. And so China Telecom cannot simply say, I have a better path to 22394, because it will not have a digital signature from 22394 saying that China Telecom is the next hop. The next hop that is identified by 22394 is to Verizon Wireless in this case. No one can say, I'm going to send your data to 22394 because it didn't have the digital signature from 22394 that includes the destination. Now, even though this solves the problem, and it is actually a very attractive way to deal with the vulnerabilities of BGP, it is still not very widely deployed, because in the internet world, it becomes actually very difficult to agree on standards and to change the way things are done. ISPs, they have their own way of doing things. These actually things are working, and so it takes a very long time to deploy any changes that are on the scale of the internet. Okay. That's it for this lecture. As usual, I hope everyone stays safe. I hope you are in good health, and we'll talk to you next time.